Newton's method for finding the zeros of a function. So the learning goals in this lesson will be as follows. First, you should be able to understand the geometry on which Newton's method is based. Second, given some function f of x and an initial guess at a zero of that function, you should be able to calculate, using Newton's method, an improved guess or an improved estimate of the zero of that function. And the third learning goal we'll put off to a later video. So let's switch over to an example here. Let's say we're given the function f of x equal minus 1 over 9x squared minus 2x plus 6, and we're asked to find a zero of this function. So you may realize quickly that you don't need Newton's method here. We could use a quadratic formula, but I'd like to use Newton's method anyway. This is a good example where the calculations are simple, and we can also check later if we want using the quadratic formula to see how close we are. Keep in mind that this function has two roots, but Newton's method only allows us to approximate one root at a time. Okay, so how does this technique work? Let's start by drawing a sketch of the function. And now, using our asymptotics technique, we know that near the origin, this x squared term will be small compared to the linear or constant term. So when graphing this, we can start off treating it as a straight line through 0, 6. So I want a straight line through here. But then as x gets larger, further away from the origin, this term will start to subtract off a growing quantity from my straight line. So that means that I'll start with a straight line with a slope minus 2, and it'll gradually deviate downward, like so. Of course, the quadratic will continue off and have another 0 off to the left somewhere, but because Newton's method only allows us to focus on one zero at a time, let's focus on this one, the positive value of x first. Okay, so this suggests an obvious technique, and that is, because of this straight line-like nature to this particular function, let's actually treat it as though it were exactly a straight line. And in that case, what we have is a straight line with an intercept that's not exactly where we're hoping to find it, but it's not too far away. So what is this straight line? Well, it happens to be the straight line that we get by this asymptotics approach, but it actually happens to be the tangent line at x equals 0 as well. So how do we calculate the tangent line at x equals 0? Well, before we write the tangent line down, first we need to calculate the derivative of the function, which will be minus 2 over 9x minus 2. And now we can calculate the tangent line of the function around x equals 0. And the general formula would be f of 0 plus f prime at 0 multiplied by x minus 0, which of course is just x. And in this case, when we plug in 0, x as 0, we get 6. And then the derivative at the origin, this would be 0, and we're left with just minus 2. So it's minus 2 times x minus 0 is just x. And that's exactly what we expected, the straight line that we started drawing near the origin. So that is our first tangent line. How do we find the x-intercept, which will be our first approximation to the 0 of f? Well, we set this guy equal to 0. So we take 6 minus 2x, set it equal to 0, and from that we find that x is equal to 3. So let's introduce a little bit of Newton's method notation. Our first guess for a root, which was a terrible guess, but it was useful because of this tangent line, was x0 equal 0. Now we've used this tangent line trick to get closer to the actual 0, and so we're going to call this improved guess x1. And so we now have a better estimate of the root. Now that we have this better estimate, we could do the exact same thing over again, but now at x equals 3 instead of at x equals 0. So what we're going to do now is we're going to draw a tangent line here, and we're going to find an improved estimate where the where the tangent line at 3 intersects the x-axis. So how do we do that? Now we need to estimate the tangent line near 3, which will be f of 3 plus f prime of 3 times x minus 3. And f of 3, we go back up here, and you can work it out for yourself, but you should find that you get minus 1. What is f prime of 3? Here you should get minus 8 over 3 when you calculate it from this equation up here, from this formula up here, and that has to be multiplied by x minus 3. And what I'm interested in is not the tangent line itself, but where it intersects the x-axis. So that will happen when this is equal to 0, and now I can solve for x. And the value that I get is what I'm going to call x2, my second improved guess at the root of this function. So if you go through the calculation, you should find that you get 3 minus 3 over 8, which is somewhere between 2 and 3. Okay, so this is the type of procedure we're going to go through in general, but we don't have to find the tangent line every single time. So how do we do this otherwise? Let's write down a general expression for the intercept of a tangent line. So if we have an initial guess xn, and we want to improve that, we're going to look for the tangent line, which is given by y equal f of xn plus f prime at xn multiplied by x minus xn. And we're interested in the next best estimate, or the next estimate of the 0, which will happen when the tangent line intersects the x-axis. So that's when y is equal to 0. So now I'm going to solve this for x. And you can go through that, but what you should find is xn minus f of xn divided by f prime of xn. And that will be the next improved estimate, xn plus 1. And we've done that twice already on the previous page here, but this is the formula that you can use in general to improve from one estimate to a next.